In looking at wavelength demodulation techniques for fiber Bragg grating based sensors, and of that we realized that one family of that is spectrum analysis, and within that we were actually discussing these diffraction and CCD based interrogator, and we were looking at what are the possible what is the basic concept behind that, and then what are the kind of performance issues that we can expect out of such interrogators. And we got to the point of defining like a typical commercial spectrometer, what the specifications are. One example for that is this interrogator that's offered by this company called Epson Photonics, wherein you can see that they are giving two different models. One is from 1525 to 1570, about 45 nanometer, they are supporting 45 nanometers, and the other one from 1510 to 1595, so that's about 85 nanometer wide. And of course, assuming that each of those gratings is going to occupy say some 1.2 nanometer width, then you can possibly accommodate 70 gratings in that. And they're talking about how many pixels they have. In this case, it's 512 pixels. And the this is the interesting part. Although you say 512 pixels and covering 85 nanometers, you would say that each pixel is probably 0.15 nanometer apart. But the interesting part is that like we discussed in the last lecture, the resolution could be better than 0.5 picometer is what they are mentioning, provided you are able to fit the points that we have collected and just interpolate more points between the actual measured points. Okay, and of course the maximum speed, like we talked about, is in the order of kilohertz, and that's because of the fact that your CCD element has to be scanned across in a sequential manner. Of course, when you go from 512 to 256, if you have lesser number of CCD elements, then your speed can be twice as much more, because you have half the number of pixels, so you can go to twice as fast. Okay, and what do we give up typically? You may not actually have the actual optical resolution, and well, the range that you are actually looking at is actually smaller in this case. Okay, so those are the typical issues when we talk about this diffraction grating based interrogator. And like we discussed last time, it is very good for interrogating several grating sensors, like what we talked about in the bridge monitoring type of situation, but only limited in terms of the rate at which they can be interrogated. Okay, now let's move on to actually let me just make some space here. So let's move on to a different type of interrogation technique. So what we would like to discuss in a little more detail today is what is called this tunable filter interrogation. So what are the how does a tunable filter interrogation work, and what are the pros and cons of a tunable filter interrogator? First of all, we realize that this is actually typically based on a Fabri-Pero interferometer, right, and we are familiar with Fabri-Pero interferometers, right. So it consists of basically two mirrors that are plane parallel with respect to each other. Let's say they are of reflectivity R each, and let's say the distance between them is L, and you have a medium with refractive index N between the two mirrors. Okay, so if you have a cavity like this, a Fabri-Pero echelon like this, if you come in with say broadband light, I'll just use a different color for that. So let's say your input, so power as a function of wavelength, it's like this, it's broadband light. We know that light actually goes in here and then it gets back reflected, part of the light gets reflected, and then over this end it gets reflected again, and then this component comes over here, and then it goes through another round trip, and that component comes here, and then further round trips, they all come together here. So if they are all constructively interfering, that's a condition that you can say is basically the round trip phase, which is given by 2 pi over lambda multiplied by refractive index multiplied by 2 times L, because it's going through a round trip. If that round trip phase is integral multiple of 2 pi, then they undergo constructive interference, and those wavelengths will actually be transmitted, right. So if you are looking at the output, we see that the transmitted intensity as a function of wavelength is going to be basically a series of peaks, right, and these peaks are separated in let me just actually represent this in terms of frequency instead of wavelength. So these are separated in frequency. If you just work this out, you will see that this is satisfied by specific wavelengths, and if you look at the corresponding frequency, and if you look at two consecutive values of m for which this is satisfied, you will see that delta nu is given by C over 2 times n times L. And it can also be shown that when we look at the transmitted intensity, that is going to go through some maximum value that corresponds to these points over here, right. It goes to a maximum value, and then it's modulated by this function 2f over pi the whole square and then sine square of phi over 2, where phi is actually the round trip phase that's given by this, right. So that is phi, and the other thing that we have is f, where f, which is called the finesse of the cavity, is given by pi times root r divided by 1 minus r. So any of the standard optics textbooks like Saleh and Tesh, or other books like that, you can actually find these expressions, right? So what does this finesse mean? Well, the finesse, clearly what we are saying is the finesse goes high as a function of R, right? As you increase the reflectivity, this cavity supports more number of round trips, and then this interference condition becomes more constrained, and in other words, these peaks become more narrow as a function of finesse. And that is actually denoted by where this peak goes to half its value, or rather where this particular each of these features goes to half its maximum power, and that is actually what is called the full width half maximum width. And the finesse is such that this is also equal to delta nu over small delta nu. Delta nu is the spacing between the different what I call the longitudinal modes of the cavity, and that is corresponding to what's called the free spectral range. So the free spectral range over this full width half max is what this finesse is. So if we consider R equal to, let's say, 99% reflectivity, okay, if you find out what is the finesse corresponding to this, is pi times root of 0.99 divided by 1 minus 0.99, and if you work that out, you will find that it's corresponding to about 312 value. And what that means is your FSR is 312 times larger than delta nu. Or if you want for the same delta nu, if you want even narrower line width, you can go to even higher reflectivity. For example, if you consider reflectivity of 99.7%, you will find that this corresponds to roughly about 1000. Okay, so what that also means is your full width half maximum is 1,000th of this free spectral range. Okay, so that is going to be an important aspect, because as we will see, these transmission peaks, this is actually the transmitted light. So these transmission peaks would be used to interrogate a grating, okay, and the width of this transmission peak, each of these longitudinal mode actually determines the resolution with which you can capture the individual Fabri-Pero, individual fiber Bragg grating resonance. Okay, so that's what we will look at next. So, for example, if we consider the case that we had over here for bridge monitoring, so we talked about requiring 110 nanometer spectral width. So we need to be able to capture spectrum across this entire band. And how can you do that? Using a tunable filter. Essentially, if this is the spectrum that's coming towards the receiver, you need to essentially have a tunable filter whose peak can be swept across all these all the spectrum, right? So you can as you sweep it across, you are actually making up these points. right. So, you will get all these measurement points, and then from that you can make up your spectrum, right. That's what you are doing as far as this tunable filter interrogation is concerned. You are actually sweeping this filter in front of the receiver. So, you are picking up information content at one point at a time. Now, in this scenario, it is very important that this delta nu has to be as small as possible, hopefully smaller than the width of the FBG itself, so that you can have multiple unique points measured as far as the spectrum is concerned. So, so let us come back here and then try to capture all that information. So, for the bridge monitoring application, delta lambda is equal to 110 nanometer. So, what does that mean as far as this filter function is concerned? You want to make sure that there is only one peak that is present within that 110 nanometer. So, going back to this picture again. So, we are basically saying you have one peak here, and the next peak should happen somewhere beyond this only, right. So, you should not have two peaks within this entire spectrum, because that will end up giving you some uncertainty as to what you are measuring, where you are measuring, and so on. So, you need to have only one peak within that entire spectrum, and that means when we look at this, that the free spectral range has to be now 110 nanometers. Now, we know at let us say a measurement wavelength of 1550 nanometer, if you want to find the corresponding delta nu equal to C over lambda square delta lambda, okay. And if you plug in the values, so this is 3 into 10 power 8 divided by 1550 the whole square in terms of nanometers, and delta lambda is 110 nanometers. So, you have something in the order of so this is basically nanometer square, and then this is nanometer. So, that cancels. So, you have inverse nanometer. So, if you do the math, you will find that this corresponds to about 13.7 terahertz. Okay. So, you need to actually have a delta nu, that is the free spectral range of 13.7 terahertz. Okay. And if we consider you have a finesse of 1000, like we said, if the reflectivity is 9.7%, we can support a finesse of 1000. That means your delta nu, that is your FWHM of each of those longitudinal modes now corresponds to 13.7 gigahertz, this divided by 1000, right. And if you work this out in terms of picometer, you will find that this corresponds to about 11 picometers. Okay, basically you can plug this back in here, and then you can find out you can plug this back in here, and then you can find out the corresponding small delta lambda, and that is actually 11 picometers. So, so what are we talking about here? So, we are essentially looking at having a transmission peak for the tunable filter. So, if you are looking at the transmission as a function of wavelength, let us say, then we have one peak, and that will have to basically tune across this range of 110 nanometers, okay, and this actually has a resolution of 11 picometer, okay. So, so that is essentially how we can use a tunable filter. So, the corresponding setup is going to look like this. So, if you can use say a broadband source, okay, use a broadband source, and just like before, you send it through a circulator into these string of gratings, so on, right. But whatever is back reflected now, what we need to do is to send it through this Fabri-Pero cavity. So, essentially this fiber would have to come in here, and then you would actually have a mirror here and a mirror here, and then whatever is transmitted from this cavity. So, this is a Fabri-Pero tunable filter whose response essentially looks like this, and the output of that now is going to go into a power meter. So, you will essentially scan across and get the entire spectrum, and you will identify the Bragg wavelength corresponding to each of these sensor gratings, and based on that you can tell what is the perturbation at each of these points. So, then the question is, how can you build a fiber based Fabri-Pero interferometer? Well, you can do that provided you can actually have a fiber like this. Let us say it terminated over here. So, this is the core region and then the cladding region, and then in the facet of the fiber, let us say you are putting a coating, mirror coating on that, and then you can bring in another fiber, make sure that these two are aligned with respect to each other, and have another coating over here, okay. And so, this actually forms the Fabri-Pero cavity if it is perfectly aligned, and then if you are able to change the position of one fiber with respect to the other fiber, then what you are doing is actually you are changing the free spectral range, but if you are monitoring just one of these peaks, you will find that the peak is going to move around its whatever its position is, original position is. So, that is essentially how you can tune that filter. Now, how do we do this precisely? Well, what you can do is you can mount this on a piezoelectric element, right. So, this is actually a PZT, and then apply a certain voltage to this PZT, in which case it will PZT will expand, and since it is bonded over here, that will essentially change the position between the mirrors, and that is what is going to make it a tunable filter. Okay, so so as you tune this, like we talked about, as far as the power meter is concerned, if you are looking at the power as a function of what is the rate at which you are tuning, so you can actually calibrate that to a certain wavelength change, and like we looked at before, so you are making this measurement and you are constructing this spectrum. So clearly, if one of these grating is so from that spectrum, basically you can figure out what is lambda b1, lambda b2 and all that, and based on some perturbation, this lambda is going to change, and corresponding Bragg wavelength change if you are picking up, you can figure out how much is your perturbation. Okay, so this is the principle of how to use a tunable filter for this interrogation, and this is something that's now commercially available. So one example of that is this Fabri-Pero fiber Fabri-Pero interferometer that's made by Micron Optics, essentially like we showed, two fibers whose ends are coated, and they could, depending upon the mirror coating, they could support wavelengths in this range, but the key thing that we want to look at is what is the free spectral range that you are interested in for your sensor system, and what is the finesse you are interested in. Clearly, you need to have higher finesse so that you can achieve better resolution, but higher finesse will probably cost you a little more. Okay, so those are the kind of typical specifications that we look at when you are getting this tunable filter. Now, once again, if we go back to this, one of the things that we are interested in is how fast can we tune across this 110 nanometer thing, and how quickly can you interrogate all the gratings, and if we can actually look at one grating separately, you can just keep monitoring one grating and then switch to another grating and all of that. That is actually not going to be easy, because now you apply a PZT, it's going to sweep across all the gratings and get to that point. So it is essentially like a sequential tuning is what you're getting, but the tuning speed, typically these PZTs have resonances in the order of tens of kilohertz. So if you want to get a linear response, you want to keep it to 10 kilohertz or even lesser than that. So those are the kind of tuning speeds that you can get. So you can achieve, the bridge monitoring application we were looking at, we wanted this entire scan done within 1 second. So if you are doing it 10 kilohertz, let's say, then you can actually do 10,000 points within a second, and so you can do that with the resolution of possibly 11 picometers in this case. Okay, so both of these techniques are actually fairly good to measure the entire spectrum, right? Both this tunable filter interrogation and the diffraction grating based interrogation, they are very good to measure a wide spectrum with a large number of grating sensors. Now, if you want to do this for only a few number of grating sensors, and if you wanted to do true dynamic sensing, then this is actually not going to work out very well. So the spectrum analysis is typically for quasi static sensing, right? So that's actually over kilohertz, but it can handle really a large number of sensors at a time. But if you wanted to go to true dynamic sensing, right? If you wanted to go to dynamic sensing, and if you don't have that many number of gratings to interrogate, because if you have only a few gratings, the cost that you incur in doing the spectrum analysis is it's not something that you can justify very easily. So you would want to actually go to a technique where you can actually deal with a fewer number of gratings, and it can be possibly more cost effective. And that's what we are looking at when we are discussing this matched or edge filter technique. So let us see what this is about. So if we look at matched filter or edge filter interrogator. So we just quickly looked at why we need such interrogators. So these are useful for dynamic sensing. As in the case of one example is acoustic emission monitoring, where you are trying to pick up strain changes in the order of 10 kilohertz to 1 megahertz. Okay, so these are basically ultrasonic waves that you are trying to pick up. So why do we need such sensing? Well, one of the key applications for this is structural health monitoring. And so let me take a couple of minutes to tell you a little more about what structural health monitoring is about. Now, whenever you have a capital intensive structure like an aircraft, for example, then you want to make sure that you can keep the aircraft free from defects, and or maintain it such that you can have it free of defects, and then if you do regular maintenance, you can possibly increase the lifetime of that sort of a structure. So when we talk about structural health monitoring, what we see typically is when you look at the cost of maintaining a structure as a function of, let's say, test frequency. So if you're looking at test frequency, you can go to two extremes. One is test frequency is high, that you are doing tests very frequently, or it is low, or you almost never do any testing. Okay, so clearly the cost of doing such testing, it's going to change according to this. So if you're doing high frequency of testing, then the cost is going to be very large, but of course when you don't do much testing at all, then the measurement cost. So this is actually the measurement cost is going to be quite low, right? On the other hand, there is something called operation cost, and that is actually how much do you pay for maintaining the structure, and also taking care of repairs and all of that, right? So if you do a high frequency of testing, you actually make sure that things are not actually there are not many faults, or even if there are any faults, you can take care of them when there is when they are actually relatively small, minor in nature, right? So you can you don't incur a lot of cost when you do minor repairs. But on the other hand, if you don't do much testing, then you may not know that there is a fault that's developing until it becomes a really large fault. So in which case you'll have to incur a lot of costs. So if you're looking at the operational costs tend to go like this. So this is the operational cost, okay. So overall, when you look at this combined cost, the combined cost is going to be something like this, okay. And we can clearly define 3 different regions of operation. So one is what we are calling as in this case it's basically corrective maintenance. So only when a fault happens, you actually do the maintenance, right? Because you are not testing very frequently, right? So you may actually end up doing the maintenance only when there is when you have a large fault, and the other side is what you can call as preventive maintenance. So you're not waiting for a fault to happen, so you are being very proactive. You keep testing very frequently, and you can take care of faults even when they are relatively minor in nature, okay. So those are the 2 extremes, but we clearly see that if it comes to the total cost, neither of these are actually optimum, right? So what you really need is what is called condition monitoring. So if you are monitoring the health of a structure frequently, and you are keeping track of whatever if there are any faults developing, you keep attending those faults, you can actually work at this optimum point, right? The right test frequency, and you can also look at it in terms of the magnitude of the defect. So the magnitude of defect is likely to be small over here. It's likely to be large over here, right? So you can say, you can also look at this in terms of the defect size. So the defect size is likely to be small over here and large over here. You may not actually pick it up before it becomes very large, right? So you want to make sure that if you are doing some condition monitoring, when you're working in this regime, you are working in this optimum sort of regime. So that's what structural health monitoring is all about. You can actually, a subset of structural health monitoring is what is called this condition monitoring. And when it comes to condition monitoring, there is something else that you want to keep in mind. So when you look at the structural health as a function of time, okay, we know that the structure is going to maintain its health when it's relatively new, but then it's only a matter of time before it starts going down, okay, which of course you can what you're trying to do with condition monitoring is, if its condition monitoring is done properly, then you can possibly extend, right, the lifetime of the structure. So this is enabled by condition monitoring. So the question is, what do you monitor? What sort of signatures do you monitor to understand the health of the structure? So let's take an example of a motor, right? If a motor, you monitor the structure health to the point where it fails at some point, okay. After some time of operation, it completely fails. But before it fails, it would have actually given you some indication, and that is basically some audible noise, right? Some audible, some acoustics it would have basically given. And even before that, you could actually get some thermal signatures, right? If some part is actually, some moving part is developing a fault, maybe it will heat up a little more compared to other parts. And so if you're measuring temperature, you can actually say that this part is going to fail if it's going to be operated like that for further time. And even before that, you can actually get some signatures in terms of its vibration. So the if there is a fault developing, if you look at the vibrational modes of the structure, you will probably see some changes in that, and based on that you can say something is abnormal about this structure, okay. But even before the vibration sets in, you typically have these acoustic emissions, or rather you can say these are ultrasonic waves that are emitted. So these are the waves that we are talking about, 10 kilohertz to megahertz type of frequencies. So if you have an ultrasonic sensor, you have basically an early warning to an impending failure. You can pick up the defects early and then take some action related to that, and then you can possibly go on this curve, okay, if you can pick up defects at early enough. So this is actually the this ultrasonics is the earliest precursor of any abnormality which can possibly lead to failure, okay. So for a lot of applications you want to be able to pick up ultrasonic waves. Now just look at this for a second. Are you able to pick up some audible sounds? Yeah, possibly, sound waves are nothing but pressure waves, so they are going to, if you have a fiber Bragg grating exposed to those pressure waves, the fiber Bragg grating is going to get stretched. So if it's put on a substrate, then as the pressure waves are hitting that substrate, it's going to stretch the fiber Bragg grating, and then you can pick up those audible sounds. Is it capable of picking up temperature? Yes, certainly. If you put that on different parts of the motor, you can actually tell what is the temperature at those local points. Is it possible? Can you pick up vibration? Yes, you can do that also. That's actually quasi-static type of strain signatures, which you can certainly pick up as well. And above all, what we want to see is, can we actually pick up ultrasonic waves using this? Now, clearly, when we talk about ultrasonic waves, the fiber Bragg grating itself, we are subjecting it to, so this is just the periodic structure, and we are subjecting it to some let's say there's some ultrasonic waves that are hitting this, and based on that it will basically stretch and compress. So according to the frequency of the waves, you are going to have a back reflected wavelength, which is going to just move back and forth in wavelength corresponding to these waves that are incident on that, waves that the grating is exposed to, right? So you can certainly, the grating itself is sensitive to that, but how can you pick that up using an interrogator? Clearly, if you are using an interrogator like this tunable filter interrogator or the diffraction grating based interrogator, these are limited to kilohertz rates, right? So they are not going to be very good for this type of application. So you need something else. So what is that something else? Well, you can actually go for what is called edge filter interrogator. So essentially you have a broadband source, once again, right? Let's say it's going through a circulator and then it's incident on this grating, and the back reflected light now, let's say you are putting it through a edge filter. Well, what is an edge filter? The edge filter will have a transmission as a function of wavelength that is going to look like this. Okay, so the transmission actually changes as a function of wavelength. So if you have something like this, then if there are any perturbations at acoustic at this ultrasonic frequencies, so you have all these perturbations here. So correspondingly, it's going to change the transmission of this filter, okay, and correspondingly you will have all these the transmitted intensity is going to change as a function of time. Okay, so what you can do now is from the edge filter you can put a power meter or a regular optical, let me just, instead of calling it a power meter, I'll just say it's a optical receiver, right? So once you have made this demodulation, then it's directly picked up by this optical receiver, and the frequency at which you can pick up these oscillations. These can be very slow oscillations or very fast oscillations. Irrespective of that, you're going to have the corresponding change over here. Okay, so it's only going to be limited. So the detection frequency only limited by the receiver bandwidth, right? So you can pick up frequencies even up to megahertz reasonably easily. Okay, so how are you able to do it? So what is this edge filter? Well, that edge filter is nothing but a dielectric filter stack. Now you must have seen this in some other introductory photonics course, where if you have alternate layers of high and low refractive index, right? So you say NH, NL, NH, NL, and if you come in with a wave, it's going to, anytime there is a change in the reflectivity, it's going to go through a reflection. A part of the light is going to go through a reflection, and whenever it's going from rarer to denser medium, there is going to be a pi phase shift. Okay, and if you make the thickness such that there is a pi by 2 phase shift that's incurred while going through this, and that you can ensure by making 2 pi over lambda nh multiplied by dh equal to that you are making it pi by 2, which means that dh equal to lambda over 4 times nh, right? So if you make it this thickness, then it can give a pi by 2 phase shift, but it is going to once again undergo reflection here, but it's going from high to low, so the reflection that you undergo here is not going to incur any phase. It's because it's going from denser to rarer medium, and then of course when you look at what's coming here, this is once again pi by 2, so what's coming here is going to have a pi phase shift. Similarly, if you have another pi by 2 phase shift over here, in this layer there is going to be a pi phase shift, and there's pi by 2, another pi by 2 here, and when you look at this is going to be 3 pi, right? So similarly you can say another pi by 2 here, reflection here, pi by 2 here, and that is also going to be 3 pi. So all of these are either 0 or 2 pi or integral multiples of 2 pi phase shifted. So they are all going to constructively interfere, and we know that's how we can make a dielectric mirror, wherein more number of these high low pairs you have, more will be the reflectivity that you get. Okay, so that reflectivity depends on the index contrast and the number of pairs that you have. Okay, so imagine that you're going to have to make an edge filter like this, you basically say, okay, at lambda 1 you have a certain transmission, at lambda 2 you have a certain transmission, lambda 3 you have certain transmission, and so on. You can define all these things. So essentially you make this one structure for lambda 1, and then you have another structure for lambda 2, and then you have another structure for lambda 3, and so on, right? So effectively lambda 1 is low transmission, so this should have high reflectivity, so you have more layers that are reflecting that are causing a reflection at lambda 1, and then for lambda 2 it has higher transmission, so lesser reflectivity. So that means this is going to have lesser number of layers, and lambda 3 is going to be still lesser, and so on. So you can basically concatenate multiple dielectric stacks, and through that you can actually achieve this edge filter response. Okay, so that is this is actually a very simple way of doing the wavelength demodulation. So it could be quite cost effective as well. Once you are able to make this filter coating, you make it on a large substrate, so you can you can dice it up and get several filters like this. So the cost of this could be relatively small compared to some of the other things that we looked at previously. However, it does have a limitation. The limitation is if you wanted to interrogate multiple gratings, then you need to have, so if you want to put one more grating over here, then you need to have, for that grating you need to have a separate filter and all of that, and that is going to, it's not impossible, but then it's going to make this design quite complicated. Okay, so this edge filter design is not very scalable from that perspective. Okay, so that would be the drawback of something like this, and that could possibly be addressed by this other technique called a match filter technique. The idea is like this: you are trying to interrogate a Bragg grating, the response of a Bragg grating. Why can't you use another Bragg grating to do that interrogation? Okay, so that is essentially the key thought as far as the match filter integration is concerned, which we will look into more detail in the next lecture.